My group has decided to work on dengue virus for this assignment, and dengue virus is an arthropod-borne virus and it has a total of 4 serotypes. So in the past, dengue virus can only be found in tropical countries. However, it has now spread worldwide, affecting non-tropical countries as well. So currently, more than 1 billion people are living in dengue endemic regions. So for this assignment, we have first searched for the DNA sequence of the 4 serotypes from NCBI, and we have obtained the FASTA format of the sequence. So the accession numbers are as listed. Our main objectives for this assignment is to assess the variability of the 4 dengue serotypes, and since virus mutate over time, we aim to find out the evolutionary change in dengue serotype nucleotide sequences across countries. And lastly, we aim to observe motifs present in the 4 dengue serotypes. So first, we decided to run cluster omega, which is a multiple sequence alignment, to check how similar the 4 serotypes are. So this is a progressive alignment method, which is a heuristic approach. So unlike dynamic programming, progressive alignment does not ensure the best alignment. However, we can ensure that the task is completed in meaningful time. So there are actually 4 main steps in progressive alignment, and this include first, pairwise alignment of all combinations possible. Number 2, setup of identity profile and guide tree. And number 3, progressive alignment. And lastly, output of the phylogenetic tree. And this slide depicts the output from cluster omega. So we observe that majority of the segments are highly conserved, as depicted by the numerous asterisk displayed. However, there are a few regions which are not as conserved as the rest, and this include alignment position 300 to 311, 2841 to 2853, and 4939 to 4950. And also, the output of the phylogenetic tree showed that dengue virus 1 and 3 actually share a common ancestral lineage, which is of interest to us. Therefore, we decided to run a local alignment using Smith-Waterman algorithm.
So, since we have established the fact that there is a common ancestral lineage between DNV1 and DNV3, we next go on to do a test specifically for these 2 sequences only. And the test would be the pairwise sequence alignment using Smith-Waterman algorithm. We're going to use local alignment specifically because it works best for most sequences. It aligns segments of the sequences which are similar, and there is no end gap penalty to it. So after running this test, we found out that there is 72.2% identity and similarity between DNV1 and DNV3. So moving on to our next objective, we will be finding out the evolutionary change in sequences across countries. To do so, we are going to use basic local alignment tool, or BLAST for short. Basically, BLAST allows us to search a query sequence that we have entered against the database of NCBI, and the results will show us other highly similar sequences in the database. And basically, when the results appear, we are going to find this value called e-value, which in very simple terms, it means the false discovery rate, where the value, if it's lower, it is the better for us to trust the result. And as seen in the parameter set for this test on the right side, we could see that we are going to optimize the results for only highly similar sequences only. For the blast test, we are going to use DNV1 first. Basically, we are going through the blast test in chronological order. So DNV1 is our query sequence for this particular one. Basically, after running blast, we found out that the strain from Taiwan, it's 98% identical to the one they've entered, which is DNV1 from the NCBI. Same goes for Indonesia and South Korea. The strains from these 2 countries, they are 97% identical to the NCBI nucleotide sequence of DNV1. And all 3 results shows that there is an e-value of 0. So basically, we can say that the false discovery rate is low. It's actually 0, so it's non-existent. And therefore, they are good hits and we can trust these results.
After placing the DNV2 sequence found
on NCBI into BLAST, we found that the DENV2 isolated from different regions of Thailand is 98% identical to the DENV nucleotide sequence. Also, since the E-values are 0, therefore false discovery rates is low and thus they are good hits. We did the same for DENV3 and the results from BLAST show that the DENV3 isolated from Singapore from 2004 to 2005 is 99% identical to the NCBI nucleotide sequence that we put. Also, since the E-value is 0, false discovery rate is low and therefore they are good hits. We placed the DENV4 nucleotide sequence found on NCBI into BLAST and found that DENV4 isolated from Indonesia, Haiti, and the US are 99% similar to the DENV4 nucleotide sequence that we entered. Also, since the E-value obtained is 0, this means that there is low discovery rate and therefore they are good hits.
We utilized the 4 protein sequences to identify motifs present in all of the dengue serotypes. We used ScanProSite to allow us to scan proteins for matches against the ProSite collection of motifs, as well as against our own patterns. For the parameters used, we excluded motifs with a high probability of occurrence from the scan. Our output gave us 24 hits by 6 distinct profiles on all our 4 sequences, a considerable amount of motifs present to infer that they are biologically similar to a certain extent. Our BLAST results indicate that DENV isolated from various countries still retain similarity for each serotype, making it easy for scientists to track the spread and evolutionary change of dengue virus globally. We conducted multiple sequence alignment and received a significant amount of conserved regions depicted by the asterisks. But there were also regions in the serotypes with common ancestral lineage which did not have near 100% identity. However, DENV serotypes are considered closely similar and conserved. From the ScanProSite results, we were able to find a considerable amount of motifs in profiles of the 4 serotypes. And from the multiple sequence alignment results, we found many conserved regions between the 4 DENV serotypes. So to conclude, our results gathered from multiple bioinformatic tools show that dengue virus serotypes are highly similar between one another as well as respectively. This may provide insights for future scientific studies on dengue virus with regards to the relationship between the 4 serotypes. Knowing this information, there is a better chance at understanding how the dengue virus works in relation to each serotype, paving the future for more meaningful research on the dengue virus to be carried out, with the aim of reducing its impact worldwide.